Okay, happy Valentine's, everybody. Speaking of which, before I forget, make sure that you have some kind of recognition. Valentine's Day. Yeah, that one is mainly carbohydrate and lipid. Pretty high punch of calories for its size, but that's what makes them fun, I guess. All right, the only other thing I see on the calendar is coming up, I mentioned this for the last time, Quiz Force still due on Friday, so if you're planning to hand it in person, of course, you'll need to do that some other time than on Friday, because we won't be here. You can put it in my department mailbox if you want to, if you don't want to run it by Blair Hall, or you can scan it in and put it in the Dropbox, D2L. Yeah, that's about it for the course kind of things, other than to keep up and stay on schedule. All right, and before I forget, I know we're already out of the carbohydrates official section, but, excuse me, you can probably see this better if I come a little closer. Talk about a viscous carbohydrate. Anybody used rice syrup before? Okay, they make it by starting with rice starch and hydrolyzing it. So they're starting from the big end of the molecule and whacking it down to smaller pieces. But it's they hydrolyze enough glucose polymers to make it actually sweet. This stuff is not quite as sweet as honey, but it works kind of like honey, made from rice like that. I mean, you can stand like this and you have to wait several minutes before it wants to come out. And what got me to thinking about this was, at home we kind of turned Valentine's Day into more of a prank day than anything else. But so the prank is we make this Rice Krispies treat, and you know the way they're usually held together is with marshmallows, which is why they're white and so forth. Okay, so our glue instead is a 50-50. I'm going into way too much. So it's a quarter cup of rice syrup. I'm sorry, that's a half. Half a cup of honey, and 1 cup of peanut butter, and 8 cups of Rice Krispies, and a little bit of salt. Okay, this makes the sweetness, and then you mix it with peanut butter, and that makes the fat, so the lipid. I just realized there is a connection to what we want to be doing. Okay, so that's our way of gluing together the Rice Krispies treat. So, that recipe is never going to market. I see. The public as a whole will have no interest in this whatsoever for Rice Krispies, but that's kind of our prank version of a Valentine's Day treat. And then just to make this combination of flavors totally incompatible with something else, you top this off with the chocolate mint. Chocolate mint and peanut butter, those usually do not mix, right? Okay, so nobody's going to scoop us and take it to market, make a lot of money on it. Yeah. All right, so finally on topic here. Am I recording? Yeah, recording. We talked about the structures of triacylglycerols, and now here are the properties. This will be important to you, especially if you're working in nutrition. So we'll look at the physical properties and break it into 2 categories, the saturated and the unsaturated. Okay, the saturated ones, which are chemically simpler, I guess you'd say, are the ones that tend to be solid at room temperature, and they're usually derived from animals. So this would be things like suet, tallow, which is usually sourced from beef, lard, that would be pigs. Actually, there is a plant version, which would be Crisco. That one's actually made from a plant by a reaction that I think we'll get to. Then the unsaturated ones are the ones that tend to be liquids at room temperatures, and we call them oils just because of the physical properties they happen to have for us humans at room temperatures. And those would be your plant oils, what you'd expect. Do they teach you these days which ones are the preferred ones nutritionally? Do they say the unsaturated ones like canola and olive? Is that still a thing? Okay. Those are probably the most popular ones, but also soy oil, corn, and so forth. Those are all viable. They just have different profiles, and they're very different from each other chemically. So the physical properties, the main ones you're going to be looking at are solid or liquid at room temperature, and you can guess something about the source. So here's some chemistry to go along with fats, and the first one to know about is hydrolysis. Okay, so why do we talk about this? Chemically, here's what it is. Hope you remember a little bit about this from your organic class. This is just adding water. In the process of doing that, you're going to break esters. And that takes you, at that point, back to your glycerol, which is the backbone of the whole thing, plus the fatty acids. All right, this reaction right here happens in digestion. Turns out that fats are broken down, then they're absorbed, and then they're reassembled, which is kind of an odd process, but be anticipating this. This is a real reaction that you've seen in organic before, and just to put names on the characters, here's what you'd be looking at. Here's glycerol, and here's your fatty acids. And come to think about it, since this reaction invokes 3 water molecules, it had better invoke 3 fatty acids if you're degrading the whole thing. So that's one kind of reaction that's basic to triacylglycerols. Tearing them apart, the calorie gaining feature of fats comes from this portion right here. You could eat an awful lot of glycerol and not gain a whole lot of weight, but fat should pack a lot of it in to a small space. Okay, and then here's the other thing to know about, and this is hydrogenation. And I've picked one out here that has several different spots in it, so you can track what happens. Well, there are several things that can happen. So why would anybody want to do this? This is done to take something that is liquid and to make more of a solid fat. That may be a little bit of an oversimplification, because some manufactured grades of hydrogenated fats are still liquids, but they have different frying profiles. The companies that do this reaction, adding hydrogen to oils, don't just start out to make one product. They've got several different ones in mind that'll have different melting points, so they go in different kinds of food. And these are usually used for food products where if you eat it, you kind of know what you're getting, and you don't care too much. Like, if you put partially hydrogenated soy oil in a Twinkie, it's like, well, maybe that's the least serious problem with the Twinkie. Just go ahead and enjoy the Twinkie and don't eat too many of them. But here's the kind of thing you'd be looking at. Let's see if I can track. Compared to the starting material, the reactant is no different, okay? This one right here, what we're saying is, just for comparison, this one doesn't react. And then let's choose another one here. This one right here, so that'd be 1, 2, 3, 4, 1, 2, 3, 4. That spot right there, that one adds hydrogen, which is the reason people do this reaction. Manufacturers do it because they're trying to make something a lot more like this. So in some cases, though, depending on how much hydrogen you add, you may starve it and on purpose leave a little bit of it unreacted. This version would still have some liquid character to it at some temperature. Maybe you want a fat that melts at a different temperature than others. Then there's some other spots where it looks like you've got something weird that happened. This spot right here, and I'm going to try to stay out of the molecule itself. This does react. And so I'm going to do the comparison here. It reacts, but instead of adding hydrogen, it isomerizes to an isomer that I would like you to name. You started out here in a form that I'd hope you'd recognize as cis. And so this one also reacts. So there's nothing more to say about it. There's just this one odd spot. It's cis to begin with, and when you come down here, do you recognize that that's trans? This is what you get. That's the configuration of an alkene if you're just like drawing the whole chain uninterrupted and you put a double bond into it. The main chain goes in on one side and out on the other. So that makes this a trans isomer. This portion makes the whole thing a trans fat. There are no naturally occurring versions of that compound with a trans spot in the chain. No plant or animal sources that I'm aware of, and that means that we have no natural enzymes, fat-degrading enzymes, that are adept at handling this. You have to kind of wait around for these things to isomerize inside your body or react otherwise before the natural enzymes can handle them. So they tend to build up. They're hard to metabolize. That's why they've got the reputation that they do. So just going into this, there will be chapters on the whole function, storage of fuel. So this would be both oils and fats. The plant, the corn plant, the canola plant, or what have you, makes oil in its seed because it is planning to use that seed to sprout and make another plant somewhere down the road. And so the oil was not made for you or for me. The plant was making it as energy storage. Got to have this in mind to sprout the seed and give the seed enough energy to get up to where it's sprouted and making its own energy photosynthetically. That's the idea behind an oil. Fats, yeah, they're for storage, right? That's their unpopular function in humans. That's the way we store energy, no question, and it has a good purpose if it's not excessive. Insulation, walruses, many of your polar animals have an extra layer of fat, and that keeps them warm more easily than without it. Okay, that'll be it for now, though, for that level of looking at triacylglycerols. Okay, here's another one. This one is not so important for metabolism. It's not so important for your diet, but oh my, talk about structurally important. So phosphatidates and phosphatidate esters. Now here's what's similar about them to what you've already seen. This group of lipids is also going to be based on glycerol. The core will be the same. You have 3 carbons, each with an OH. You can expect to see that unit somewhere in the middle of the molecule. This first example right here has your glycerol right there. So here's what's different about them and the triacylglycerols that we've been through. This one is drawn oriented so that it has 2 kind of different zones of the molecule. You can think of this one as the tail, and heads up here, this one is only 2 esters, not 3. And that leaves space on the remaining oxygen, the third one in glycerol, for something else. Well, this is an ester, but it's an ester of phosphoric acid. Okay, just to be sure, I'm going to color all of the oxygens that you can say are part of the glycerol backbone. So it would be those three. Two of them look like where we've already been, triacylglycerols, and the phosphate is a new version. This whole structure amounts to something that will have an important role in membranes and so forth. It has two features. There's the charged head group, and that's the phosphate. So maybe I should put that here as well. There's the phosphate head, and it's charged, and then the other one is the exact opposite. It's a greasy nonpolar tail. All right, that's a signal that you're looking at a molecule with two very different zones to it. The next one is kind of similar. Imagine starting with that phosphate framework, and instead of one of the oxygens, you swap out other groups. Nature does this all the time. Okay, this right here is your big difference. The X group right here can be several different things, and so let me just identify them as the tail. So this will be a charged head, and it will still have a nonpolar tail. And I just realized we need a positive charge on that nitrogen too. All of them will have a charge somewhere. This oxygen right here in the carboxyl group, that'll have a negative. Yeah, nature does this by design. One of these, this one, phosphatidylethynolamine it's called. You've had some exposure to this one. You probably didn't know what the structure was. Anybody ever heard of, what's this brown liquid, not wheat germ, what's the other ingredient they get by milling wheat, and it ends up getting used for baking? It's kind of like a detergent. What? Molasses? It's not molasses exactly. Molasses is a sugar. It's a carbohydrate. Lecithin. That's what I'm trying to think of. You can get that stuff, and it's good for baking if you're trying to compatibilize a lot of water and a lot of oil. So it gets, you'll see it thrown in as an ingredient in some health foods for sure, and I don't know to what extent big commercial baking operations run it. But lecithin is kind of a detergent. It's good for compatibilizing oil and water. And you can see why it would be. The oil part of any ingredient you've got in your food is going to mix with this. The water will mix with this. It's a way of tying very different ingredients together. Okay, so that kind of anticipated the properties, and this, I suppose you'd say, would be most important in a cell membrane. But just to get going on that, think of them maybe as just one molecule at a time in two different zones. So within any one molecule, you're going to have two regions, and that's even without worrying about binding it with anything else. That's just within the same molecule. They're often abbreviated, drawing-wise, like this. You'll see this part right up here. So there's the polar head group with its charges, and then the tails are just drawn as some kind of abbreviated squiggles like this. Now there would be two of them in the version that we just drew here. Let me make sure we're connecting this. That's this molecule right here. drawn as an abbreviation. Okay, phosphatidyl. This is a phospholipid. And so what do? Well, if you know what they look like one at a time, it's not a big jump to getting to what they look like if you put a whole bunch of them together. So if you do that, here's what you're looking at. Imagine several of these things lined up. So the head groups all tend to identify each other, stick together well, be compatible with water, and arrange themselves in a zone. So here would be outside the cell, and here there would be lots of water. Okay, then each one of these, this will take some drawing, that's okay. Each one of these features two different long tails. And you know, having seen the exact structure of that diester, you know what those tails are. They look like that. And then they have found a way to partner up with molecules below them. That is the beginning of a cell membrane. Okay, tails to the middle, heads to the inside and the outside. Okay, I'm drawing them kind of randomly on purpose. It's not like a one-to-one sticking to each other. Okay, and then what you've done by assembling anything with this kind of shape is you now have an area that's different on the inside and the outside. All of that just from this little lineup of hydrophobic tails. Okay, this is like taking corn oil and throwing it into water, and the corn oil kind of wants to sit on the surface in a thin layer. But imagine turning that into a structure that now becomes its own container and is capable of holding a whole bag of enzymes and fuel molecules and DNA and everything all into one spot. The closest big analogy I could think of would be a plastic bag. Okay, that's an honest to goodness layer. It will hold stuff, but it sure didn't assemble itself, and it sure isn't this little. It's much bigger molecules. So that's why, you know, a cell membrane really is a piece of chemistry that is, we all take it for granted. We've seen these diagrams, but it's much more sophisticated than you might think. So here we have on the inside, we have two lines of tails, and then on the outside you have charges, plus, minus, whatever you got. That faces the water. That's what a cell membrane is chemically. Now there's more to it than that, and we will get more to it in the course, because if your cell membranes were nothing but lipids, they wouldn't be strong enough. They need an addition of protein, and they need an addition of cholesterol just to make the whole thing more rigid. But that's where you start. It's a sandwich. It's mainly lipid. Okay, and then there's another comparison to be aware of, and that is, here's what happens as a comparison between just your fatty acids all by themselves. Okay, fatty acids. What's their structure? Remember, it's this, some long R group, and they have a carboxylate end, straight out of your organic class, and you'd have some cation. So let's say sodium. So their salts, what we're saying is they form micelles. Notice what they don't form. These things are just little blobs. They don't form membranes. So here's what they would look like, and there's only one tail per molecule, so I'm going to start abbreviating them like that. You get a region where a whole bunch of these things has accumulated, And they start to find ways to poke their tails all together. And all of their heads start to kind of circle the wagon. I realize this isn't the most beautiful diagram. But what you do is you establish the structure where they've kind of put, in the interior, they've put all of their hydrophobic spots. And the resulting shape is spherical. That's a nice polite way to describe it. So what you have is all charged head groups are now pointing out. All the R groups are on the inside. And they don't function as cell membranes. But there is something really practical to know about them. And that is, this is why soaps work. They put oil in the middle, and that's why it gets carried away. There are lots of versions of making this work as a soap. Does anybody here prefer plant-based soaps like Castile and some things like that? You like it, Kaylee? Okay. It will have, I've tried several different ones for nerdish reasons, I admit. But, okay. A plant soap will have a different feel to it than a synthetic soap. Most of them that you buy these days are just plain synthetic. They work, they just don't feel the same. A Castile soap will, Kaylee, if you're one of these that prefers it, at least sometimes, what do you like about it? Is it it leaves a different feel behind? Yeah, it's they're getting more and more expensive. And again, I track these for nerdish reasons. You have to start with a big vat full of olive oil. No way around it. Reflux it with sodium hydroxide. No way around that. And then do an isolation procedure that gives you the soap. So it's not trivial to do. But there are handcrafted soaps that people make that are specialized in their sources. There may be allergenic reasons to do them. Okay, so that's, in other words, that's not a cell membrane. They're practical. But phospholipids are the ones that do form bilayers. And here's why we care about them. They work in entire cell membranes. You wouldn't get a soap molecule to do this. And just to totally clean the whole thing up now, I'm going to make it much more generic and much less molecular. What you have here is a nonpolar zone. And on the two sides, this region is polar, so is this one, and it's drawn and kind of discussed as if we're talking about a cell membrane, but it's more than that. It can be the nuclear membrane, it can be the membrane around a mitochondrion. Any membrane you want to talk about biologically has this one theme: nonpolar to the middle, polar to the outside. And then the game becomes, okay, now I've got my membrane to start with, but let's say that it's a mitochondrial membrane. What do I have to do to that to decorate it up to make it function differently from a cell membrane? As you all probably know, mitochondrial membranes have the function of making energy, which is what mitochondria do for the cell. They have very different helpers, even though they all start with the same thing. So you start with this, add other characters. Okay, enough about lipids. Category number 2, and here's number 3. Steroids have this structure right here, and the way you would describe these chemically is you'd say that you have some fused rings. So I guess we're looking at 3 6-membered rings, just one 5-membered ring. And they share an awful lot of edges. That is the core that is found in all steroids. Now, there may have been considerable monkeying with the ring chemically. Just to pick an example, take these first two right here. This first one is estradiol. It's the naturally occurring estrogen in all humans, in fact all vertebrates. And it follows the theme, but the first ring was made aromatic. So the biosynthetic pathway that makes it removes hydrogens from here, leaves that whole first ring flat, planar, and with a phenol on it. The other one is testosterone. This one is not aromatic, it's a ketone. And both of them have the same chemistry out on the right-hand side of the ring, an OH. I hope, though, that what you would conclude just by looking at these things is what would you say about their solubility? You're eyeballing them, and let's count the carbons. So there's 6 on the first ring, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. I just went around in the route that they're normally numbered. So that's 17 carbons in the basic core of every steroid. So look at all those carbons, and then look at either one or both of these molecules right here and make a prediction. Do you think it ought to be water soluble or not water soluble?
I think it's soluble.
It needs help.
A little bit, because the
There's two lone pairs of electrons on each of the oxygens, and there's a hydrogen on each one. So that could form like 6 hydrogen bonds. The general rule of thumb for water solubility is for it to go in quickly and well, you need no more than 3 carbons per OH group. That's why glucose is so soluble. It doesn't dissolve quickly, but once you get it in, it's happy to stay in water. This thing has so much CH on it that it needs help to dissolve in any aqueous solution such as blood. Blood is mostly water. All on their own, they don't want to dissolve in blood. Okay, and for that reason, these molecules are not present in very large amounts in any of us. It's tiny, tiny, millimolar, nanomolar levels. And I guess that's a good thing, because you sure don't need much of either one of them at the level of the endocrine system to make a big difference. Right? You're talking about minute differences in the ratio between these having big, big effects. They're signals. They have effect on tissues that are very subject to hormonal regulation, and so that's why you don't need or want very much of either one of them. The fact is they ride around on proteins, so kind of like Stephen was suggesting. If you give them the right protein to transport them, they'll get around. But left to themselves, they dissolve in water just a little bit, which is all we need. You don't want any more than that. So that's one thing they do, regulate development of secondary sexual characteristics. They also regulate metabolism. Here's one you will have heard of. Cortisol, everybody heard of that one? Okay, and please, no structure required. That one we'll get to eventually, I hope. But what you don't want to do, I should put this up in the title, you don't want to memorize these. So please don't go memorizing the stereochemistry of the OH group on carbon 17 and estradiol or anything like that. That's not the point. They're greasy molecules, don't dissolve much in water, just a little bit, and that's all you need. That's all you want. Although I am remembering one time a student, undergraduate, who was doing research with me, gave a presentation at a conference. And my research in those days focused on ways to put groups here and here. Turns out the estrogen receptor will tolerate substituents here. So that's not 6, that's number 7. 7 and 17. And you have to put them in just the right location, down. So they need to be axial. And the estrogen receptor will tolerate them. The reason people care about that is estrogen is a double-edged sword, right? So if you're female and you get to menopause, this level drops, and that's both good and bad. It's good because it lowers your risk of breast cancer, but it's bad because it increases the risk of breaking bones. Okay, some of you have relatives, I'm guessing, who are in this dilemma right now, right? You heard that? You're getting older and you get a bone density test. It's like, oh no, what am I going to have to do now? My bones are getting thin. So there's this chemical search for the, quote, ideal estrogen. The hope is to find a synthetic estrogen that would have all of the benefits and none of the drawbacks. So a patient loses her natural estrogen. If you can find the right supplemental estrogen, it would hopefully not promote breast cancer, but it would also promote strong bones. So there must be thousands of graduate theses out there on deposit in chemistry department libraries. This graduate student has made 2 more derivatives. Okay, the whole career of this grad student was making 2 more derivatives of estradiol and testing them to see what kind of effect they had. First task is get them to bind to the estrogen receptor. That's step number 1. The ER, as it's called, is a really picky protein. So I was in that discipline for a while, and the story I was getting to is an undergraduate went with me to give a seminar, and she did a nice job of talking about the group we were trying to attach out there. And then somebody asked her after the presentation, okay, so what's the next step? What would you envision doing with this group you developed? So she asked for a piece of chalk and proceeded to draw the whole structure of estradiol, got all the stereocenters right, got the point of attachment of the group right, and everything like that. And I was kind of surprised myself that she remembered this whole structure and wrote it on the board up there so beautifully. And everybody was like, no more questions. If you can remember that, you obviously know what you're doing, and okay, go ahead, please do it. That was one of my favorite moments. She gave a really good answer. Okay, so that's steroids as regulating, and we've got to just talk about a couple more functions here and call it done. So this is another function that doesn't maybe get headlined as much as some of the others, but this is a steroid. Once again, you can tell by looking at the core that's a natural detergent. This would be in the small intestine. Okay, I hope you can see that there's kind of 2 zones to this molecule. There's like all of that, and then there's this. So the first one is going to be miscible with fats, and this little region up here is going to be soluble in water. Okay, so that's the reason that this is valuable biologically. So this helps dissolve, or at least emulsify, fat that you eat. Now, this is something that's, as you probably know, secreted out of the gallbladder. Anybody know what the liquid secreted by the gallbladder is called? bile. Yeah. Okay, so there's this mixture of compounds. This is an important one. And it's a detergent. You make your own. And then I saved the best one for last, just to make sure that we cover the fact that there is a good role for this molecule that everybody hates. This is cholesterol. All right, and notice what's important about it. In that zone right there, you can have something, you can tell by looking at it, it's these 4 fused rings. There's going to be no flopping around in that zone of the molecule. Now here, this part, remember free rotation around carbon-carbon bonds. Remember your Newman projections, those funny little things? That's happening all the time, every day, in every cholesterol molecule in that part, but not here. These things are so tied down that you can honestly call this zone in the molecule rigid. So it strengthens cell membranes. And which part of a cell membrane do you suppose this sits in? And by the way, let me add one thing. Yes, this OH group isn't charged, but it's still a polar head group. So that's going to want to point down either into the inside of the cell or sit on the surface or something like that. This is going to strengthen cell membranes, and sorry, I'll just wrap this sentence around. And it does that by sitting in the nonpolar zone. Okay, now that's starting to make a cell membrane more complicated and more like the real world. It's not just a row of lipids like we started a few pages back. That's where you start, but then you come along and you add this into it, and for good reason. This is like rebar in concrete, if any of you have seen concrete construction going on. It's stiff and it's going to keep things more stable, so the membrane is less prone to just dissolving and floating away. There'd be no point in a membrane like that because it wouldn't be a bag that held everything together. Once you put in this kind of reinforcement, now you're talking. Okay, it's getting stronger. Then along come the protein components that make it even stronger yet. You've got to start somewhere. This would be kind of like your component number 2 to make a good cell membrane. Okay, I think what we'll do is say the end for the day is right there. On schedule, we should be... Yeah, we're good. We're on schedule, so let's just call it done and hope you have a good Valentine's Day, and hope somebody gives you something more impressive than one Hershey's Kiss. In the office where I work, one of the offices where I work, we actually had today a first in my career. We had a singing Valentine show up.